We live in an age of basically perfect pixels, right? Our screens, our TVs, our monitors, they're sharper and more colorful than they have ever been. So why is it that sometimes on these perfect screens, we see images that are, well, surprisingly ugly? You know exactly what I'm talking about. You're playing a game, exploring this huge open world, and the sun is setting. But that beautiful, smooth sky is just ruined by these weird, chunky, visible bands of color. Or you're watching a movie, and a dark scene isn't smooth at all. It's broken up into these distinct steps. It totally pulls you out of the moment. Well, that visual glitch, it has a name. It's called color banding, and it happens for a really simple reason. There just aren't enough different shades of color available in the file to create that perfectly smooth gradient your eye wants to see. It's like trying to paint a sunset with, only a handful of crayons. Okay, so let's get into this, because to understand why the color palette is so limited, we gotta talk about the math that's happening behind the scenes. And it all comes down to bits.
You see, almost all the digital content we consume, games, streaming videos, you name it, is made and delivered using what's called 8-bit color. So what that means is for each of the primary colors, red, green, and blue, you have 256 possible levels of brightness. So you take those 256 shades of red times 256 shades of green times 256 shades of blue, and you get this, almost 17 million possible colors. Now, that sounds like a ton, right? But when you have to stretch those colors across a giant, super subtle gradient, like a sky, you can literally run out of shades. And here's where it gets really interesting. Your fancy new TV or gaming monitor, it's probably way more powerful than the content you're feeding it. A lot of them can display 10-bit color, so instead of 256 shades for each color channel, they can handle 1,024. So what does that jump from 8-bit to 10-bit actually look like in terms of colors? It looks like this, over 1 billion possible colors. And that just lays the whole problem bare. Your screen is this high-performance machine ready for anything, but the 8-bit content you're playing on it just doesn't have enough information to take advantage of it. So for years, artists and programmers have had this brilliant little workaround for the problem. It's kind of like a magic trick for pixels that creates the illusion of more colors than are actually there. It's a technique called dithering. Dithering is all about fooling your eyes. By arranging the pixels of the few colors you do have in very specific checkerboard-like patterns, it tricks your brain into blending them together. You end up seeing a new color, an in-between shade that doesn't technically exist on the screen at all. It's a fantastic hack of human perception. And the way it works can be pretty simple, actually. A common method, called order dithering, uses a little grid of numbers, a threshold map. The computer looks at a pixel, compares its brightness to the map, and decides, okay, should this be black or white? The result is this pattern that, when you step back, your brain just goes, yep, that's gray. And I just love this quote. It really gets to the heart of it. Dithering isn't just some dry, technical fix. It's an art. It's a whole philosophy about being resourceful, about taking what you have, even if it's limited, and creating something really beautiful with it. All right, so if dithering is this amazing, time-tested solution, why are we still seeing color banding all over the place? Well, this is where our story takes a pretty sharp turn. Because that clever old magic trick, it doesn't really work on our modern high-tech stages anymore. So that's the million-dollar question, isn't it? If dithering is such a great way to fight banding, why do so many modern game developers just not use it? Why do they leave us with those ugly lines in the sky? Well, the problem is our screens got too good. The dithering trick actually relied on old TVs being a little bit blurry. That blur would physically blend the pixel patterns together. But our new LCD and OLED screens are so incredibly sharp, they reveal the trick. You don't see the illusion, you just see a distracting, shimmering grid of dots. And it gets worse. That noise pattern fights with other modern tech, causing ugly smearing, and it's an absolute nightmare for video compression on sites like YouTube. So what this means is that developers are stuck with a really tough choice. They can leave in the color banding, which is ugly, yeah, but it's static, it doesn't move. Or they can use dithering and replace it with this shimmering, distracting noise that actively messes with other parts of the image. For a lot of them, the banding is just the lesser of two evils. But this brings us to one last really fascinating point. We've just spent all this time talking about how the noise from dithering is bad. But is all noise bad? This is where we have to get inside our own heads and think about what our brains actually like to look at.
I mean, think about it. We actively add noise to images all the time. Photographers do it, filmmakers do it, we even have filters for it on our phones. We call it film grain. So what is going on here? Why is one type of visual noise considered a terrible flaw and another one is a beloved feature?
And this slide really nails the difference. The noise from dithering is a technical byproduct. It's harsh, it's a repeating pattern that's only there to solve a math problem. Film grain, on the other hand, is an aesthetic choice. It's a subtle, random, organic texture. Our brains don't see it as a mistake. We see it as adding quality. And there's a good reason why. Our brains connect film grain with the entire history of movies. It feels authentic, tangible. It gives a clean, sterile digital image a sense of life. And believe it or not, it can even trick our eyes into thinking an image is sharper. It can even help hide other digital flaws, kind of like a much more sophisticated, more beautiful version of dithering. So if there's one thing to take away from all of this, it's this. Not all visual noise is created equal. The noise that dithering adds to fix a problem is fundamentally different from the noise we add on purpose for art. One is a distracting glitch, the other is a texture our brains have learned to love. So the next time you see those bands in a video game sunset, you'll know the whole story behind them, a story of math, of clever tricks, and of how technology has changed. And it leaves us with this one last thought. In our quest for the perfect pixel, how do we decide when an imperfection is just a flaw, and when is it the very feature that makes an image feel human?